Let's go over just a couple kind of random and special cases of projectile motion and some books and some questions like to ask. One of the things is, what if you throw something off the height of top of a cliff and you put it into projectile motion? You don't throw it horizontal. A classic example is, throw objects A and B off the cliff. You're going to have that launch angle be the same angle, just one's above the horizontal, one's below the horizontal, and these initial magnitudes of velocity, the values of velocity are going to be the same. So maybe you throw this at 10 meters per second kind of up at an angle and 10 meters per second downward at an angle. And they're going to ask you, well, what's the speeds right before they hit the ground? What's the velocities right before they hit the ground? Well, actually, let's not do velocities. Let's just do speeds. Well, in this particular case, it seems tricky, but it can be answered conceptually, because if this is thrown downward at the same angle this is thrown upward, obviously this is going to hit the ground at some value at some new angle. This one, it's got to go up, and then it's going to come down. So, but if I go to the horizontal point where they were both launched, and I redraw what A is going to look like at that moment, well, because it's symmetric, this angle VA is going to look identical to VB. So all we do, if we put it upward at the same angle compared to if you were launched it downward at the same angle, all you're doing is extending the trip, but once you reach this point, it's identical. Identical. And so the final velocities in this particular case are identical, but only for this special case. If you launch from top of a cliff, if you launch the same upward angle at the same downward angle from the same height with the same magnitude of speed, the velocities will be identical, meaning the value of those velocities right before they hit the ground and the angles. Now, obviously, those velocity values are going to be greater than what you launched with because you fell, but whatever those final velocities are and the angles will be identical. Now, what we'll learn later in the year, and we'll learn why, I'm not going to tell you now, is that even if you didn't launch these at the same angle, even if you launched it maybe even horizontally, maybe these angles weren't the same. But if they're all launched at the same speed, it's not the same velocities because they have different angles, but if you launch them all at the same speed, they're all from the same height at the same time, with all the same speed, they're all going to hit the same ground with the same speed. That won't be the same angle though, so they're not all the same velocities, but they will all hit the ground with the same speed. If these magnitudes of speed are the same, all launch from the same height, they'll all hit the ground at the same speed, at different angles, but the same speed. I'm not going to go through the proof of that now. It's going to be much easier to do when we talk about energy later in the year. So that's one special case, or two special cases. The other special case is launching at complementary angles on a flat horizontal surface. So if we launched something at a, let's say, a 60-degree angle, and we launch something at a 30-degree angle, but these speeds, the magnitudes, are the same value. So let's again say 10 meters a second. What we're going to find is that they are going to travel the same amount of range. Complementary angles, again, has to be launched on a flat surface, a horizontal surface, but complementary angles will land at the same place. Again, also ignoring air resistance. And you can prove that mathematically. These values of speed have to be the same. complementary angles, launch at the same place. Now, different complementary angles are going to launch, or land at different spots. If I launch at 20 degrees and 90 degrees, or 20 degrees and 70 degrees, if I launch at 20 degrees and 70 degrees, you're going to actually fall closer to where you're launching from. Because if I go to 70 degrees, I'm going higher, but I don't have much X motion. Even though it's a lot of time in the air, I don't have much X motion, so it's going to fall shorter. If I go to 50 degrees and 40 degrees, I'm gonna go further. The one spot that is maximum, as I said before in a previous video, is 45 degrees. I know this is a little messy, but 45 degrees, since its complement is 45 degrees, goes the maximum range. It's not maximum hang time, but it is maximum range. It's the perfect balance between the amount of hang time you have versus the amount of X velocity you have to let it fly. Maximum hang time is straight up. So you're going to get no range. You get max height in the air. Max time in the air, I'm sorry. Well, max height and max time. So, those are special cases for now. That's it. All right, keep on working.